Have you ever wondered what the first days of our day are? Imagine a time when our sun was not the eternal, living star that we know today, but a stupid and powerful struggle of the universe. A time when it still found its place in the universe. The James Webb Space Telescope, JWST, has lifted the curtain on this mysterious era, revealing a world of incomprehensible energy and violent cosmic events. For the first time, we will see our sun and other stars in a new moon and discover secrets that could change our understanding of the universe forever. As JWST looks deeper into the universe than ever before, it returns images and data that are as exciting as they are revealing. These observations not only reveal the turbulent youth of stars, but also challenge everything we thought about the birth and growth of stars like our sun. What new mysteries are waiting to be discovered? What forces were involved in the early days of our solar system? And how did the planets, including Earth, form? The answers lie in the faint, distant light captured by JWST, the light that traveled through time and space to reach us. Stars are born in the dark and dark clouds of gas and dust that cover the universe, many of which are called star incubators. These incubators are the birthplace of star formation, where the interaction between energy, wind, and dust gives rise to the celestial bodies that light up the night sky. However, this process was far from peaceful. In these areas, forces are very high and create high pressure and temperature conditions. As JWST has shown, young stars are flexible. They are energetic and powerful beings capable of projecting large beams of air and energy that last for many light years. One of the most revealing aspects of JWST's observations is the violent nature of star formation. The telescope provided the first glimpse of the Herbig-Haro objects, a bright patch of nebulae associated with newborn stars. These objects occur when interstellar gas streams collide with the interstellar medium at high speeds. The shock waves produce a spectacular light show, illuminating the beginnings of a star's life that have never been seen before. For example, consider the Herbig-Haro object HH21. HH21 is located in the constellation Perseus, about 1,000 light-years from Earth, and is one of the smallest and closest examples of such objects. The JWST observations of HH21 have provided a wealth of data, revealing important details of the processes that occur at the beginning of stellar evolution. The telescope's ability to capture the faint light of these distant objects has allowed astronomers to study the composition, temperature, and dynamics of the gas and dust surrounding young stars, which presents new insights into the mechanisms of star formation. JWST observations are not just for distant stars. They also illuminate the beginning of our day. By studying objects like HH21, scientists can draw parallels between these young stars and the sun in its formative years. The similarities are striking and suggest that our sun also entered a period of active activity, characterized by strong jets and strong wind currents. This discovery is important because it provides a window into the past and helps us understand what our solar system was like more than 4.5 billion years ago. In its infancy, the sun was probably surrounded by a disk of gas and dust when the planets formed. JWST's ability to observe these early stages of stellar evolution allows us to reconstruct the environment in which the sun and its planets were born. Studying Herbig-Haro objects such as HH21 reveals the challenges faced by young stars in their early stages of development. The powerful jets emitted by these stars can disrupt the surrounding accretion disk, potentially preventing the formation of planetary bodies. It raises interesting questions about the processes necessary for planet formation and what influences the evolution of planetary systems. By observing these processes in real time, JWST will help scientists refine their star and planet formation models, bringing us closer to understanding the origins of the solar system. One of the most exciting discoveries made by JWST is the role of magnetic fields in the formation and evolution of stars. Magnetic fields are a major force in the universe, creating the dynamics of accretion disks and controlling the outflow of material from young stars. JWST's observations have provided new insights into how these magnetic fields interact with the surrounding environment, influencing the direction and strength of the jets emitted by young stars. Magnetic fields are important not near young stars. They also play an important role in the overall process of star formation. In regions of strong magnetic fields, they can direct the flow of gas and dust and expel material toward the forming star, helping to form the structure of the molecular cloud that surround it. This process is important in star formation, as it determines how much material a star can form and ultimately determines its final mass. JWST's ability to observe these magnetic fields in action has opened new avenues for research in astrophysics. By studying the interaction between magnetic fields and star formation, scientists can gain a deeper understanding of the forces that control the birth of stars and the evolution of star systems. This knowledge is important not only for understanding the origin of our sun, but also for predicting the behavior of other star systems around the world. Another important contribution of JWST to the understanding of star formation is its ability to study the chemical composition of gas and dust in star-forming regions. Advanced optical instruments can detect faint light signals, allowing astronomers to analyze the elements and molecules in these regions with great precision. One of the highlights of JWST's observations of HH21 was the discovery of complex molecules in the rays emitted by the star. These molecules, such as carbon monoxide and silicon monoxide, are indicators of energetic activity in the star and its immediate environment. The presence of hydrogen in jets is surprising, as it provides new insights into the chemical composition and thermodynamic processes at the beginning of stellar evolution. These findings have important implications for our understanding of the chemical processes that occur during star formation. By studying the composition of the gas and dust in these regions, scientists can learn more about the conditions that lead to the formation of stars and planets. This knowledge is essential to understanding the origins of life, as the elements and molecules found in these star-forming regions are the building blocks of planets and living organisms. JWST's observations are not limited to individual stars and their structures. The telescope's ability to observe distant galaxies and other cosmic phenomena will provide new insights into the broader processes of cosmic evolution. By studying the light emitted by distant galaxies, quasars, and other celestial bodies, astronomers can trace the history of star formation and the evolution of galaxies around the world. One of the amazing things about JWST's observations is its ability to look at the regions where stars were in their infancy. These star universities are scattered throughout the galaxy's planetary laboratories where the process of star formation takes place under extreme conditions. Understanding this process is important because stars are not just celestial bodies. They are the basic building blocks of galaxies and the sources of the elements that make up planets and life itself. JWST's instruments, such as the Near-Infrared Camera, NIRCam, and the Near-Infrared Spectrometer, NIRSpec, are specially designed to detect the faint infrared signals emitted by young stars and their surroundings. Infrared radiation is particularly useful for studying these regions because it penetrates the thick clouds of dust and gas that cover the star-forming regions and reveals the hidden processes within. One of the key findings of JWST is the accretion of material to young stars. When a young star emerges, its energy pulls in the surrounding gas and dust, forming a rotating disk called an accretion disk. This disk plays an important role in the evolution of the star, as it provides the material from which planets form. JWST's ability to study the chemical composition and dynamics of these disks shed light on how planetary systems like our own solar system formed billions of years ago. The accretion process is a simple balance between the energy of the star's wind and the external pressure of the gas and dust. When the material falls on the star, the energy is released as radiation, which heats the surrounding disk and creates a powerful outflow of gas. These streams, or jets, are one of the main features of young stars and play an important role in the evolution of the star and its surroundings. JWST observations of these jets have provided new insight into the mechanisms that drive them. By studying the chemical composition and temperature of the gas in the jets, scientists can learn more about what happens at the beginning of star formation. This knowledge is necessary to understand the nature and evolution of stars and planets, and to predict the processes necessary for the formation of lifelike planets. Magnetic fields also play an important role in planet formation. JWST observations have shown that magnetic fields are important not only in shaping the dynamics of accretion disks, but also in controlling the formation of planets in these disks. Magnetic fields can affect the direction and speed of the wind and dust flowing into the star, affecting the distribution of material in the interior.